Put the board down.
O precisamente yo lo tengo en Spring con Physics 2. Me estaba moviendo.
I'm gonna try a new thing here. So I'm gonna use this recording this time because some of you said that there's a problem with the sound. So I'm gonna try this recording. I'm gonna put the notes here. So let's see if this is. I'm gonna also write on the board, so just like so you guys. It's not a good idea. Is there a way to make that?
You have to put down the
But I think I was writing the board on the board, but maybe we can use the just the recorder. So let's stop this. Turn off the projector. So 2 weeks ago we started to talk about the dynamics of rigid bodies. So we will spend the whole month of April talking about how the dynamics of rigid bodies look like. You guys remember we talked about if we have a rigid body translation, it will translate, and if a body's translating, it deals as a particle, like it applies the same concept, the same equations that we have from before for the velocity and acceleration is gonna apply the same. Like to, if you guys remember, the velocity is the time derivative of position, and the acceleration is the time derivative of the velocity. All these rules are gonna apply the same. And then last time we started talking about the fixed axis rotation, which is kind of a new thing. So we talked about rigid body fixed axis rotation. I introduced the concept, but we didn't solve an example. But let me introduce the concept in 5 minutes again. So if you have a rigid body like this, and this rigid body somehow is attached to a bar, and this bar is rotating about this point, like this body is rotating this way. So we take a cross section in this body and look down. This is gonna let me show it something, for example, not sure if you guys can see, but it's gonna be a circle like this. If I take the cross section here, this is gonna be something like this. And this body is rotating about the dotted axis here, so you have omega, something like this, and maybe alpha is something like that. So if this is my x-axis, my y-axis, this is going to be my z-axis. So if I want to describe the position of any point, like let's take a point on this body on the surface, on the outside surface of the body. Let's assume this is my rigid body. I'm going to make a point on the surface from the outside. So this point is going to be, for example, here. So if I want to describe the position, because when we talk dynamics, if you guys remember in particles, we need to talk about position, we need to talk about velocity, we need to talk about acceleration. So if I want to describe this position, in particles we use S as the position from an x-axis or something. So the S, the distance, is 10 meters, and the position it changes to 11 meters, so the change in the position is 11 minus 10, so it's 1 meter. But here, this body has an axis rotation, so I describe the position of this body from my origin by the angle theta measured from the x-axis. So this is theta. So position, we call this angular position. Yeah, we call this angular position, number 1. angular position, we describe it by theta. There's difference between angle position and angular displacement. So what is the difference? Angular displacement. Angular displacement, so displacement means there's a change in the motion, change in the position. So the point B at this location right now, but after a few rotations, maybe this point B went to another location. So the difference between the final position and the initial position, we call this d theta. And when I say angular, that means theta is included, and we call this d theta, the change or the angular displacement, which is the change in the position of the point on my rigid body. The second quantity that we need to define is the angular velocity. You guys remember what is the angular velocity?
It's like omega. Omega.
Omega, but what is the definition of it?
It's equal to
Hmm?
d theta over dt.
And what is the physical meaning of d theta over dt? This is the time rate of a change of the angular position. So we want to track, because when we say velocity, so it's a time rate of a change. Something is changing over time, which is a distance. And since I say angular, that means it includes angle in it. So it includes theta. So omega is d theta dt. Okay, same thing, angular acceleration. What is the physical definition of the angular acceleration? It's a still time rate of a change, but time rate of a change of what? If it's a linear, exactly. If it's linear, so it's the time rate of a change of the linear velocity. But since we talk angular and we have fixed axis rotation, so it's the time rate of a change of the angular velocity, and we call this alpha, and alpha is d omega dt, and we can write it in a different way. If you guys remember, we can say d omega d theta, and we can have d theta dt. So this quantity is the same like this quantity. You can cross d theta with d theta, you will be left out with d omega dt. However, this formula is gonna give me this as a function, so I'm gonna remove the time component. So this is giving me this as a function of omega d omega d theta. Sometimes in the problems with fixed axis rotation, I'm gonna give you a problem that doesn't have a time component. So you need to take the time out. So alpha is equal to omega dt, but my problem doesn't have time, so I have to use omega d omega dt. Okay? Alright, so this is the rules, and if you guys remember that we have equations similar to the linear motion, like right now we have omega, which is d theta dt, and we have alpha, which is d omega dt, and also we have alpha, which is omega d omega d theta. We can use that three to get the equations motion. This way. Right, so we have these three equations. We can use these equations to get the equations in the equation sheet that we have, and you will find them here. You'll find the general equation, which is these three equations, you will find them here, and you can integrate them to get the theta, to get the omega, to get the alpha, and you will have a special case if the acceleration is constant. It's the same thing from the linear movement. Okay, so that's what we talked about last time. I was doing like a quick refreshment. And also, we talked about something else. We talked about what if I want to derive the linear velocity from the angular velocity? For example, like let's look at this circle here, this circle. This is the center of this circle, and actually this is the x-axis, and this is the y-axis, right? And here we have point B. This is circle, is the cross section from here. I'm looking at over there. And we have B, and this B at a position theta, and if this B is a changing in position by d theta, B is gonna be here. This angle, we are gonna call it d theta. But what if I wanna find out the velocity here, v? Since we are talking linear velocity, so we need to find out how to convert the angular position to angular displacement. So how can I find the displacement from this point to this point? If you want to find this, you want to find the arc length, this arc length, right? This is S. So if I want to find V, V is going to be equal to ds dt. How much linear movement that this particle or this point make from here to here? So I want to find S. What is the value of S? You guys remember how can I get the value of S knowing that this radius R and this angle d theta, this is going to be equal to? Exactly, so it's going to be R d theta. Same thing when we get the perimeter of a circle. What is the perimeter of a circle? It's 2 pi, all the angle, multiplied by R. So this S is just, this is small, so it is just this angle in radian d theta multiplied by R. But if I want to find a quarter of a circle, so it's going to be pi over 2, which is the 90 degree multiplied by R. If I want a half of the circle, it's going to be equal to pi multiplied by R. If I want to find the perimeter of the entire circle, it's going to be 2 pi R. That's geometry basics. Do you guys understand that? So if I want to find the base and arc length of a circle, so you find the angle in radian of corresponding to this R and multiplied by the radius R. This is very, very important rule. You shouldn't forget it. Okay, so we have S R d theta. So if I want to find the velocity, the linear velocity of this body, so I have to take the time derivative ddt of R d theta. So I'm going to replace S and put R d theta. And since R is constant, I can take R out. So this is going to be d theta dt. And I know the time derivative of the angular position with respect to the time, or the time derivative of the angular position, is equal to omega. So this is going to be omega multiplied by R. You shouldn't forget this either. So the velocity V is equal to the angular velocity. So the linear velocity is equal to the angular velocity multiplied by the radius. Okay. This is as a quantity, but what if I want to find them as a vector? So the velocity vector is equal to the angular velocity vector cross product the R vector. And we talked about this last time. So if this is moving this way, this is the direction of the omega. If the direction of the omega is counterclockwise, so the direction is going up. So this is the omega direction because the omega is this way. And R is going this way down, like R is something like this. This is R vector. So if I want to find the cross product, so I have to use the right hand rule. So we use the right hand rule in two ways. First, if we want to, like you have omega is rotating this body this way, so the direction of the rotation is going up. So this is one way to use the right hand rule. But if you want to find out the cross product of this vector that is going this way and this vector that is going this way, you have to take them like this, and the cross product is going to be perpendicular on both of them. Okay? But what if I want to cross product this vector by this vector? So this one needs to rotate like this, so it's going to be this way. Okay? Alright, so same way here. I want to cross product omega. Here's the order, is very important. R multiplied cross product by omega is completely different in direction from omega cross product by R. Because here's the omega, I take my hand from the omega and I go all the way down to R, so the cross product is going to be this way. It's going to be something this way. This is going to be V. But if omega is in the different way, like if omega hypothetically is going down, something like this. If omega is going down, so if I want to go from the omega to R, okay, let's actually, when you do this, let's, so that you guys can imagine it. So all I'm saying is this, I'm not sure if you got it. So omega, so that means it's gonna go inside the board. So omega vector and R vector are on the board. So if I'm doing like this, so this is going inside to the board. So when I write this, I mean by this is going inside. This one is not on this wing, it's going inside. If I want to do omega multiplied by R, this is going outside of the board. Okay? So inside and outside. Just can't do it 3D in a perfect way, but this is, I believe, the best way to do it. But if I want to do it this way, so that means that V is going this way, on the other direction, right? Okay, so here's my rule. V is multiply omega by r. And the next thing that we did last time is that we need to get the acceleration out of the velocity. So how can we do that? Just want to make sure that I didn't. Right, there's something else about omega multiplied by RB. I also explained it last time, but this is, I believe, the most important part, like this rule. The next important thing is how to get the acceleration from this. What is the definition of the linear acceleration? Right now I'm talking linear acceleration, not angular acceleration. So if I'm saying linear acceleration, I need to take the time derivative of the angular velocity or the time derivative of the linear velocity. Linear. So I want to take A is going to be equal to the dv dt, right? So I want to take the derivative of this. I have two quantities multiplied by each other. So what should I do? I differentiate the first and multiply cross product by the second. So this is going to be d omega dt cross product r plus omega cross product dr dt. Okay?
Product rule? Chain rule or product rule?
This product.
Product.
So d omega dt is this quantity alpha. So we have alpha vector multiplied by the r vector plus you have omega dr dt. Actually, this is the definition of the velocity. Okay, so s is the same like r. Okay, so you have omega cross dv.
So the first one with alpha is cross product with r?
Hmm?
So alpha times r or is it
Alpha cross product r.
Where's
Right. So you have here is multiplied by v vector. We can write the acceleration in different ways. So the acceleration vector is going to be alpha cross product r plus omega cross product. And actually I know that v is omega cross product the r vector here. Okay? So this is the definition of the acceleration. I'm not sure if it's in the equation sheet. Let me double check. Yeah, everything is in the equation sheet. All right? The last thing is this component is going to give you the tangent acceleration, the tangent, and this component is going to give you the normal acceleration. This is going to be as a quantity alpha multiplied by r, and this is going to be omega squared multiplied by r. So for example, if you have like the r vector is going this way, this is the r vector, and you have omega is this way going up, that means the rotation is this way. So if you multiply them together, it's going to give you a velocity vector this way. Okay? So this is the velocity vector when you multiply omega by r. It's going to be this way. Next is I want to multiply the velocity vector by the omega vector. So here's the omega, and this is v. So the acceleration is going to be, the normal acceleration is going to be something like this, the a normal. So let's do this here. You have a disk like this, and it's going to rotate about this point. And I have, for example, the omega is this way. So if the omega is this way, and I stretch it here, a line, so the velocity is going to go up or down. Logically, without any multiplication or any cross product. It's going to go up, right? Because the omega is this way. So this point, definitely, the velocity is going up. If you want to go do r vector and cross the product of the things, it's going to give you the same direction. So, okay, how about the normal acceleration direction? As we agreed before from the particle dynamics, always the normal acceleration is going to go this way or the other way. Go inside, right? So this is a n. So v is going up, and I have omega, like if you want to draw the vector of the omega is going to be something like this. So this is like, so the omega is this way, if I want to translate this omega and put it here, this is the omega. So let's cross product. This is V. This part is V vector, which is this part. Let's cross omega by V. Omega is like this, okay? So I got my hand with omega, and I go all the way up to the V, so the AN is gonna go inside. So that's proof that what we are doing is right. Okay, so that's, I believe, most of the rules that we need for now. And if we wanna find out the absolute acceleration, so if I'm asking about general acceleration, and same concept apply, like if I say in the problem that this point is accelerating with 2 meters per second squared, is that a tangent or a normal acceleration, or a total acceleration? Tangent, normal, or total? If I'm saying in a problem, this point is moving with a velocity 3 meters per second squared and accelerating with 1 meter per second squared. So I'm saying accelerating or decelerating. Is this a tangent or a normal velocity or a total? When I say accelerating, that means it's a tangent. Normal velocity doesn't have anything to do with the body accelerating or decelerating. So when I say body's accelerating, so it's always tangent velocity. But if I say the total acceleration of the point is this, so that means that it's a total, which is the square root of a tangent squared plus a normal squared. Okay? And one thing on the side, do you guys remember what is the rule of the a normal from the linear acceleration? Yes, right? AN was the velocity square over rho, right? What is rho? It's the radius of the curve, right? What is v? It's the tangent acceleration. Same thing here. Look. En is equal to v squared over rho. What is v squared? V squared is omega multiplied by r. Squared then over rho, which is equal to the r. So this is going to be omega squared r squared over r. It's going to give you omega squared r, which is this one. So it's the same thing. Okay? All right.
Sir, how did you remove the cross products and simplify it, like AT and AN?
Okay, so if we want to find the quantities, like the quantity of the product, so you multiply this by this. So this is going to give you, this is the magnitude. If you want to find the direction, the cross product is going to give you the direction. But this one actually is tricky because there will be change in the direction. But what I put here is the magnitude. You need to find out, is it going inside the positive direction or in the negative direction? We're going to look at an example and see if it's the positive k or negative k. So what I did here is just the magnitude, but directions are still very important. All right, so let's talk about another concept that, or to make sure that we understand the movement of rigid bodies. Yeah, we're gonna do it. But I'm gonna explain just something. So let's see this mechanism and understand the movement. So let's say, for example, I have a bar like this. Okay. This is a bar, and attach it to another bar like this, and there is a bin here, and we have another bar this way, and attach it to a bin this way. And there is a hinge here, and there is a hinge here. Okay, let's imagine the movement. Let's put some labels. So I'm gonna put here A, B, C, and D. Let's say, for example, this is a mechanism. Let's say that this arm, AB, is gonna move with an angular velocity omega AB this way. Can you imagine how is the movement of the other bars, how they are gonna behave? Okay, this bar is moving this way. So this bar is gonna also push this way, and this point is gonna go down, and this one is gonna go down, right? Okay, so what is gonna happen here? Let's map all the movement. So if omega AB is going this way, can you tell me what is the velocity of B? oh sorry, I mean like, where is the direction, is this the direction is right? Or this direction is right? Which one is the right one? The first one.
First.
This one, VB is gonna go this way. And from the movement, I can imagine that omega DC is gonna be this way. Tell me, C is gonna go down or gonna go up? Down. And it's why I make it perpendicular, because if you guys remember from last time, if we have a fixed axis rotation and this point is fixed, so all the movement, like this, the velocity at C is gonna be this way. And the velocity here is gonna be this way, and the velocity here is gonna be this way. So the maximum velocity is the more that I am out of this center, and it gets less and less and less until it becomes zero at the bim, right? Do you guys remember this?
Yeah.
We did it last time. So this is VC, it's gonna be this way. And why is that? Because we said that the linear velocity V is equal to omega multiplied by R, right? The R has the same omega DC, but what it changes is the R. The way that I am away, the more the R gonna be increased and the more linear velocity that I'm gonna have. At point D, the R is zero. R is measured from point D so that the velocity is equal to zero. We call this center ICZV. ICZV. What is that? An instantaneous center of zero velocity. An instantaneous center of zero velocity. However, in this case, it is not an instantaneous center, it's a permanent center. We call it the center of zero velocity. Why? Because this point is not gonna move anywhere. This point doesn't change. But we can call it an instantaneous center of zero velocity as well. So ICZV stands for instantaneous center of zero velocity. Okay? Alright. It was easy for me to find the instantaneous center of zero velocity for this bar and an instantaneous center of velocity of this bar. Why? Because I know that the velocity here is zero and here is zero. What if I want to find out the instantaneous center of zero velocity of the other bar? This is very, very tricky. Like, for example, if I have a body like this, and you know, the velocity, this body is rotating somehow about a specific point. And for example, this point, A, has a velocity VA, and there is another point, B, has a velocity VB. I know that the instantaneous center of their velocity is always has a line perpendicular to the velocity of this point. So what I want to do, I'm going to extend a line from this and perpendicular to this velocity, okay? And then I'm going to extend the line from this and it's going to be perpendicular to this velocity. Once you do the extension and the point of intersection is the instantaneous center of zero velocity. If you want to know what is this body's rotating about, this body's rotating about a specific point here. I want to find out, you need to find 2 points with and know the direction of the velocity at these 2 points, okay? Get a line perpendicular to them. Actually, the center of velocity might be the other way. But from what I see here, it's gonna be this side. I could have extend this line here and extend this line here, but they are not gonna meet, okay? But on the other side, they are meeting at a specific point, so I know that the omega of this body is about this point. I'm gonna do the same thing here. I'm gonna make a line perpendicular to this line. It's gonna be something like this, and I'm gonna make a line perpendicular to the velocity here. It's gonna be all the way down. And the point of intersection is the instantaneous center of zero velocity for this bar. And you can find the omega about this one, and this omega is gonna be the omega BC. This body is having an omega BC. And it's rotating about a point that is very, very far down there. How did we find out? We used the VB because the thing is, what these 2 bars did to this bar, they limited its movement. How? This point was restrained by the movement of this bar, right? And this point is limited by movement by this bar. Like this bar can't, from the middle of nowhere, this point cannot, like for example, go do this movement. Why? Because it's attached to this point. So it's constrained by the velocity of this point. And this point is constrained by the velocity because there's a bend here. So VC needs to go this way and VB need to go this way. I used these two velocity and draw perpendicular to them until I found out the instantaneous of the instantaneous center of zero velocity. Why did I do that? Because in the exam I will ask you, I will give you the omega of this bar, and I will ask you about the omega of this bar. So what I'm gonna do, I'm gonna use the omega of this bar to find the velocity VB. Once I found the velocity of VB, I'm gonna find the instantaneous center here of this bar, and it has omega BC. And if I multiply omega BC by this arm, B is gonna give me VB. Okay, and I already have VB, so I can get this omega. So it's indirectly, I can get the omega of this bar. Why? Because I know this, and I know this arm, I can get this.
Can you explain that last part again, please?
Hmm?
Can you explain that last part again?
Okay, like for example, this is not a problem. We're gonna solve a problem in this. Oh, I give you omega AB. Omega AB is known, right? So what is the, I wanna get the velocity VB. Can you get it to me?
No, you.
It's gonna be this omega,
Yeah.
omega multiplied by R. Which omega? Omega AB multiplied by which R? This R. Let's say R1. Okay? So I got VB. Right. So let's get VB from different side. VB also is equal to the omega BC multiplied by R2, which is from here to here, right? So if I know VB here, like I know VB and I know R2, I can get omega BC, right? So you tell me, is omega BC is gonna be bigger or omega AB? Knowing that omega AB multiplied by R1 is equal to omega BC multiplied by R2. What I know that R1 is smaller than R2. Okay? So omega AB
Bigger or
is
bigger.
gonna be bigger than this one, so that they can be equal to each other. Okay? Alright, so let's solve an example. We are gonna do this in details. I'm just gonna give you a heads up to understand because this is called mechanism. You need to understand how this mechanism is working. Let's solve an application of this one. So we have a problem here. Example 16.1. We have a wheel like this, and this wheel is bent here. There's a pin, and there is a cord coming out of this wheel. And this cord there's a force that is pushing down, and it's going with acceleration, and it goes down. So it's saying, focus. Initially started at rest, so this wheel started at rest when theta is equal to 0. Okay, so let's say it started at rest here, at theta equal to 0, and this point at some point came here and cut distant theta. So at rest, at theta equal to 0. And then a force is applied to the cord and gives an acceleration A is equal to 4t meter per second squared. This is a linear acceleration. The acceleration of the cord, like the acceleration here, is that a tangent or a normal acceleration? I'm saying here, here's the wording. If a force is applied to the cord and gives it an acceleration A, 4t per meter squared. So the cord is the linear, right? It doesn't have anything to do with the normal acceleration. It's a linear acceleration because it's the acceleration of the cord. So it is this acceleration, A tangent. So this is A tangent. Okay, I'm saying 4t. So the acceleration is function in time. Is that a constant acceleration problem or non-constant acceleration? Non-constant. It's not constant, okay? All right, and then I'm saying where t is in second, determined as a function of time. Determine. Number 1, I want the angular velocity, so I want omega as a function in t. Number 2, I want the angular position, theta, as a function of t. Okay? What I'm gonna do, that's actually a very, very direct problem. How can I do it? Right now I have linear. First thing I need to convert this linear acceleration to angular acceleration. How? Look at this one, and I have a tangent. So a tangent is function of alpha and r, and if I want only the quantities, so a tangent is equal to alpha multiplied by r. Tell me, okay, why we don't use the vectors? You can use the vectors if you want, but it's gonna be a little bit complicated. We don't need the vectors here, but if you wanna do it, you can do it. Like you can say, okay, the alpha is going this way, so I'm saying it's in this direction, and the r this way, but at this problem level, I don't need to do vectors. Okay, so I have a tangent, actually it's equal to 40, and the alpha, which I wanna found, and r, okay, I give you r in the problem is 0.2 meters. R is equal to 0.2 meters. So what I'm gonna do is alpha multiplied by 0.2. I can get alpha, so alpha is gonna be equal to 4 over 0.2 multiplied by the time t. So 4 is gonna be 40 over 2 is gonna be 20 t, and this is gonna be radian per second squared. Okay, I got alpha. If I have alpha, is there any way to get omega?
Yeah.
How? So I know that alpha is the omega dt. I can look at my equation sheet, but right now I'm proving the rule for you. So d omega is gonna be alpha dt. You integrate both sides from omega node to omega and from t node to t, and then you'll find out that omega minus omega node is equal to the integration from time 0 to time t, and alpha is equal to 20t dt. Alright, omega node is equal to 0 because at rest, theta is equal to 0, everything at rest. So omega node is equal to 0, and alpha node is equal to 0, everything is equal to 0. So this is 0. So omega, when I integrate this, you guys tell me what is the value of this integration? Integrate 20t. 10t squared, excellent. 10t squared. From 0 to t is going to give you the same thing, and this is the first requirement. Omega as a function in time. Alright, what should I do to get theta as a function in time? To get theta as a function, I'm gonna do the same thing. I know that omega is d theta dt, so d theta is equal to omega dt. You integrate from theta node to theta, from t equal to 0 to t. So this is gonna give you theta minus theta node equal to the integration of 10t squared dt from 0 to t. This equation is given directly in the equation sheet. You don't have to prove it like the same way that I did. You use it right away, like this. Don't waste your time. I know that theta node is 0, so what I want to find is theta. When I integrate this, you guys integrate it for me. 10t squared.
10 over 3.
10 over 3.
T cubed.
T cubed. And that's it. Right? So that's actually the solution of the problem. And don't forget the units. This is radian per second, and this is radian. Does anybody have any question? This was a direct problem. I give you the acceleration, the tangent acceleration. You substitute with the tangent acceleration alpha multiplied by r. You get alpha. Integrate alpha to get omega. Integrate omega to get theta. Same thing. If you guys remember from linear acceleration, you integrate a, you get velocity. You integrate velocity, you get displacement. All right. Okay. So now we're going to talk about something related. It's called fixed axis rotation as well. So we will say fixed axis rotation, but different application. What is this application? It's called non-slip wheels, gears, and pulleys. No slip, gears, wheels pull. Okay, what is this? So an application on fixed axis rotation, you know guys, the bicycle, it has like a gear here and a gear there, and there's a belt. Okay, so that's an application on fixed axis rotation. Why? Because this tire has the one in the back, it rotate about a specific point, and another one rotate on a specific point. Also another application, like if you have a gear like this, like a big gear, and another small gear like this, or if you have a small gear here and a big gear here, and they are attached with a belt like this. So both of them are rotating about a fixed point. So we have here this here, same thing as this way. So this is a new application. So let's introduce some facts about this application. So let's say that this gear is gonna move around this point, like the omega is gonna be omega A this way. What is the direction of omega B?
The opposite.
This one is gonna move this way. This one is gonna move clockwise or counterclockwise? Counterclockwise. It's gonna move this way. Same thing. If you have this gear, it's gonna move this way, omega A. How about this one? This one is gonna move this way, omega B. Let's talk facts. If I pick a point at the intersection or the interaction between the two gears, what is the velocity direction of this point? Is it gonna go up or gonna go down?
Down.
Down, right? It's gonna go this way. This is the velocity. Okay? So is the velocity on this side from the gear is different from the velocity of the other side from the gear? No.
No.
If they don't slip, like if they will have contact all the time, the velocity of the 2 points on each separate one, like this, if there is no slip, they are gonna be the same. But if there is a slip, this one can slip from this one. There might be different in the velocity. That's why I'm saying no slip. Like they are not gonna slip from each other. Okay? So V in general as a V vector is gonna be equal to omega cross product R. This is the general rule of V, and if we want the magnitude, it's gonna be omega R. So V at point P here, VB can be, we can get it from two sides. We can say omega A multiplied by the radius RA, this is RA, or omega B multiplied by the radius RB. So you have this as omega A multiplied by RA or omega B multiplied by RB, and this is very important rule. This is the first one. Same thing with the acceleration. Let's say, for example, this wheel is gonna move with a velocity in this direction, but it's gonna decelerating. Decelerating, that means the acceleration is in opposite direction of omega, like alpha is on the other way. And this one is also decelerating, alpha B. What is the direction of the A tangent of point B? It's gonna go up or gonna go down? Up, right? Why? Because this is the A tangent of B. Because if the body is decelerating, definitely the acceleration is in the opposite direction of the velocity. If it's accelerating, the acceleration is going to be in the same direction of the velocity. Okay? Great. So this one is going to go up. So same way, if I want the acceleration A tangent of B, it's going to be equal to the alpha A multiplied by RA, because we know that A tangent is alpha multiplied by R, or alpha B multiplied by RB. And this is the second important equation. All right. Same thing with theta. If you want to say theta A multiplied by RA is equal to theta B multiplied by RB. So this also applies number 2. How about the A normal? Is the A normal from this side is equal to this side? Like if I have this and this is this way, this is the point. I have A normal here and A normal here. Are they equal? No, they are not equal. Why? Okay, so AN, you guys tell me, this is A and this is B. Which one is bigger? Is the AN A or AN B? We know that AN is V squared over R, or over rho, right? Okay, we know that V are the same, like V at this point is the same, V, for A and B. What is different? Is the radius.
A is bigger.
A is bigger?
No, B.
B.
Yeah.
B is bigger, right? Why? Because it has a smaller radius. If you have a smaller radius, that means a bigger AN, because rho is down. So I can say here that ANB is bigger than ANA. Why? Because I know that the velocity is constant, but the radius are different. Same thing is gonna be applied, like if you tried this with the belt, same thing, but it's different concept. Like you have this this belt, like it's gonna move this way. So this is VA, and this belt is gonna have VB, and it's the same belt. Like the belt is moving. Like if you have a belt, you can say that this. Do you guys remember when we have a chords? All the points on the chords are moving with the same velocity. Same thing. All the points on this belt are moving with the same velocity. So you can say that VA is equal to VB. Same thing with the acceleration. If the alpha is on the other way, alpha, and this is alpha. So if this is gonna be this way, so that means that this is the A tangent B, and this is the A tangent A. And you can say that same thing, A tangent A is equal to A tangent B. So the contact wheels is the same as the one that has belt or hinge. Okay, so let's solve example here. Let's solve this example. Alright, this example, I believe I can't draw it, but I'm not sure if you guys see this. So right now we have a disc. Can you guys see this picture? We have a disc, and this disc is attached to like a gear, and this gear attached to a motor. I'm gonna draw it, but I'm not gonna draw the gears. So I have a disc circle disc this way, and I have gears inside, like something inside this way that has gears, you know, like half tooth is here, okay? And this one is attached to a motor that has gears. Like I have a motor, like a small motor here, and this motor is centered here, and this one is rotating. This is actually where the movement is coming, okay? So this motor has gears, and this gears is touching here and making the big circle or the big wheel is moving, okay? All right, and the idea of this one is to lift a block here, like I have a cord coming down this way and is L, and this one is at a distance 4 feet and is moving up with a velocity v equal to 3 feet per second. I have some dimensions here. The big radius is 24 inch. The small radius is 18 inch. And the motor radius is, let's see, is 6 inches. Alright, so we need to understand this movement together. Let me spell the problem for you. It says a 6 inch radius motor. This is motor. So this motor is rotating. Drives a gear B. So this is motor A. So this is gear A, and this is gear B. Okay. Drives gear B, which is 18 inch in radius, which is attached to a cable spool. So the outside is a cable spool. 24-inch radius, load L starts from rest. So this load is starting from rest and constantly accelerate to a velocity 3 feet per second when 4 feet above. So it starts from here at rest and constantly accelerate to a velocity 3 feet per second after 4 feet above the ground. Find the acceleration here, A. Find the omega of the motor, omega A and alpha A and theta A. So what we are gonna do, we're gonna find the acceleration here. I'm gonna find all the parameters of the big wheel or the big spool, okay? And then from this, we are gonna find B. And from B, we are gonna find A, okay? So let's do it. So number one, I have some linear velocity, so I need to use linear velocity and linear acceleration equation. But I'm gonna use the keywords here, starting from rest and constantly accelerate. So I know the acceleration is constant, so I can use the constant acceleration equation. And I know at rest means that V node is equal to 0 and S node is equal to 0 and everything initial is equal to 0. I'm gonna use this. I know that the final velocity V is equal to 3 feet per second. And I know it cuts distance from this point to this point, so I know S is equal to 4 feet. Right, can you guys imagine I have S and S node, V and V node? So do you guys recall the equation that says V squared minus V node squared is equal to 2A node multiplied by S minus S node? You guys remember this? Actually, this is coming from, if you guys remember, the acceleration is equal to V dV ds. We got ADS, VDV, this gives us this, and this is A, S minus S node. I know lots of information about this equation, given from the keywords in the problem. It says, starting at rest, S V node and S node are equal to 0, okay? And I know the final acceleration after S was 4 feet, so I can say 3 squared is gonna be equal to A node multiplied by S, which is 4 feet. I can get the acceleration from here, and it's gonna be equal to 1.125 feet per second squared. You guys tell me, is this acceleration is tangent or normal? We are talking about linear, and we are saying accelerating and decelerating. So this acceleration is tangent, what we are getting here, because anything that has to do with how this velocity changing with the position and time is tangent. How I can get the normal, it's very easy. It doesn't have anything to do with this equation. You guys know that the A normal is equal to V squared over rho, right? So that's how we can get it. So V squared, I already know it, it's a 3, so 3 squared. And how much is the rho? Is the 6 inch, the 18 inch, or the 24 inch? 24 inch, because I'm looking at this point. If you want to look at this point, it's going to be the 18 inch. So it's going to be, don't forget to change them to 24 over 12 because we are working feet per second. And when you get the A normal, it's going to be equal to 4.5 feet per second squared. So we got the acceleration because I said the acceleration total. So we can say that the A acceleration is equal to 1.125 in the tangent direction plus 4.5 feet in the normal direction, and this is actually feet per second squared. So when I ask about acceleration, I get the tangent component, I get the normal component, and I put them in the acceleration format. Right now, I was able to get A here. Alright, does anybody have any question?
Why is it 24 divided by 12?
Because this is inches,
Oh.
and everything we need it to be in feet. Alright. Let me put this here. The equal 3 feet. And let's continue the problem over there. Alright, so from here I can say that the A tangent is going this way up. A tangent, and this is A normal. And if you want to find the A total is going to be something like this. This is A total. Okay, so the next step, what is requirement number B? We need the omega A and alpha A. Alpha A. Alright, I know everything about this, but I don't know anything about this and anything about this. So we need to figure out how we can get it. Alright, first I need to move from the biggest spool to the small gear. Alright, if I'm telling you that I put a gear or something on top of this paper, and this paper is rotating with a specific omega. What is the omega? Like, okay, two papers on top of each other, and they are gonna rotate with an omega equal to 5 radian per second. If this has omega 5 radian per second, what is the omega of the page on the top? 5 radian per second, because they are attached to each other. We are gonna rotate together. So, from the physics of the problem, I can say, if I found the omega of the big spool, I can find the omega of the inside one. So how can I find that? I have the tangent here, so I can say that A tangent is equal to alpha multiplied by R, right? Here. But before we get alpha, let's get omega first. Okay, so let's say V is equal to, we are gonna get to the alpha, but let's do it step by step, omega first. V is equal to omega multiplied by R. This is general rule, right? V is for the bigger disk, right? So this is what we're gonna call it, let's say this is AB and this is C. So VC is gonna be omega C multiplied by R at C. So VC, we know it's a 3. I wanna know omega C. I know that RC here is 24 inch, so I'm gonna multiply 24 over 12 to convert to feet. Then I can get the omega C. Omega C is gonna be equal to 1.5 radian per second. What is the direction of this omega? The direction of this omega is going this way because it's going up, so it's going in the positive K direction. So let's say positive. So this is positive K. Whatever, you can call it positive I, whatever you want to do. If this is a plane, like it's on the plane, so this is gonna be K. If this is on vertical, so it's gonna be I. Whatever, I'm just wanna know it's positive. Okay? Right, I got omega C, but from this I can say that omega C is equal to omega B because there are two bodies attached to each other. This disk is over this disk attached to the same body. We're gonna move together, so they have the same omega. Alright, so let's get to this one, the alpha. I know that A tangent at C is equal to alpha C multiplied by RC. A tangent is 1.125 alpha C multiplied by RC, which is 24 over 12, so I can get alpha C. Alpha C is going to be equal to 0.562 radian per second squared. And what is the direction of this? If the A tangent is going up, so alpha also in the positive K. Alright, we got alpha C, we got omega C, and I can say also alpha C is equal to alpha B. Like all the properties of the bigger disk is equal to all the properties of the smaller disk. Okay, I got this one. How can I get this one? Do you guys remember the rules that we have here at this point? Here?
It's gonna be in the opposite direction, right?
This one is moving this way, so this one is going to be moving this way. Okay? Alright, so let's find out. We knew here that omega A multiplied by RA equal omega B multiplied by RB. I'm going to do the same thing. Omega A multiplied by RA equal omega B multiplied by RB. What I know here, I know omega B, which is 1.5. I know RB, I know RA, or what I found is omega A. So omega A multiplied by radius of A. Radius of A is 6 inches, so I'm going to divide by 6. And if you want to divide by 12, divide by 12, okay? I'm going to tell you why I don't have to divide by 12 here. Here is 1.5, and RB is 18 inches. Why, if I don't want to divide by 12 here? Because this is over 12 and this is over 12. You want to do it? You can do it. So then, from this you can get omega A, which is going to be equal to 4.5 radian per second. What is the direction of the omega?
Inside.
This one is gonna be inside, so this is gonna be the negative way. So we're gonna say that this is negative A hat. Because it's gonna go inside. Same thing with the alpha, so I can say alpha A RA is equal to alpha B RB. So alpha A, I don't know it, RA is 6, alpha B is 0.562, multiplied by RB, which is 18. And this is gonna give me that alpha A is equal to 1.688 radian per second square, and this is also in the negative p direction. Does anybody have any problem so far? All what I did, I found all the information at this point, A tangent and B tangent, take them, and I got the alpha and the omega of the bigger spool, and then I transfer alpha and omega to the smaller one, and then use, the smaller from this one, and use this to get this one from these rules, because they are at contact, 2 gears at contact, okay? All right, so let's go to the last requirement. It asked me about what is the theta that this spool did. You write it here. So right now, I know the omega A and alpha A, I know all that. So you can actually use the relationship. So right now, okay, look at me. You know alpha, you know omega, and 1 theta. So what is the relationship that can link the 3 together? Here. You want to link alpha, omega, and theta. So you don't have time. We don't have any time in the problem.
So
Which one? Hmm?
You have to link them with radius.
How? No, I mean how to connect the 3 of them. You guys remember alpha is equal to omega, the omega d theta, right? And this is coming from the omega dt, and then we did some math. So this is the one that has 3 of them. So this is gonna be omega, the omega, alpha, and theta, and can integrate those. And this is gonna give you this equation. Half omega squared minus omega naught squared is equal to alpha A multiply theta minus theta naught. That makes sense. When you integrate this, it's gonna be alpha theta minus. And why did it use this? Why did it take alpha outside? Because in the problem they said it constantly accelerates. So I used the constant acceleration form. So I took alpha outside of the integration. I integrated d theta from theta naught to theta. They give me this. And once I do this, so everything that is known is going to be 0 because we started at rest. I have omega, so you have half omega. And I want omega A. You guys can tell me what is the value here?
1.688.
Omega A. Oh, 4.5 squared. Omega A.
Yeah, 4.5.
Yeah, 4.5.
4.5, yes.
The alpha is 1.
0.6.
1.688, and this multiplied by theta, which I don't know. Then you can get theta. You know everything, so theta is going to be equal to. When you put everything is a negative, because right now you have this negative 4.5, because you'll have to use the directions negative, and the alpha is also negative this way. When this is getting squared, this negative is going to be gone. So theta is going to be equal to negative 6 radian. Okay? And that makes sense. Why? Look at here. If this is going into the positive direction theta, the motor is going to make negative direction theta. So everything about the motor is negative. Omega, alpha, theta is negative. It's in the opposite direction of this one. Okay? All right. So that's everything about this problem. Do you guys have any questions? I solved other questions here, so I would recommend you to look at these problems. I did also different shapes are rotating with each other. Look at this problem and solve it. And also I did one with spill. So also see how did I do it. Okay, there will be some problems in the textbook. You might be look at them. So what I'm going to do with you right now, I'm going to do an application. It's called absolute motion analysis. Always focus on the problems that are being solved in the class. This is the first thing that you do when you have an exam. Like when I say quiz or when I say midterm. As you guys see, in both midterms, I included problems exactly from the class. This is the first thing that you look at. Okay, because when I'm putting the exam, I look what I did in the class. I did this problem, I did this problem. How about I take this one, do a little bit of changes. Sometimes actually I give it reduced, like I don't ask you to start a problem from first thing. Like if you guys remember in the exam, same problem that I solved in the class. I have a ball, it is hitting a wall. Okay? In the class, we did it how? I asked you to do like conservation of energy first, so that you get the hitting velocity. I give you the hitting velocity right away in the exam, so you don't do history stuff. Okay? So always focus on the problems that is in the class first, then the homework, then do whatever you want. Okay? Alright. So there's something called absolute motion analysis. And this is when you have something that is not only rotating but also it's changing in length. How? Like let's say for example, you have a window in your house, something like this, and this window is like, you have a glass, something like this. And there's a hydraulic arm. And this arm can increase in length to open this window. Can you guys imagine this? So this one is the one that can increase in length. So it can rotate and can increase in length. So we cannot actually say that this length is constant. However, this last length is constant. Why? At some point when this is closed, this arm is gonna go inside and this one is gonna close up here, okay? So there is some change in the geometry of the problem, but there's some dimensions are constant, some dimensions are changing. So let's look at them. So this is, give a different color. You have here, is this it changing? This is the window, it never is gonna change. Like this is the opening, it's gonna be constant. So this doesn't change. How about this distance? Does it change? No, it is this, it's constant because this attached to this point and this point. This is the only changing variable. So let's look at this triangle. You have a triangle like this, a line, and there's an arm, and there's something like this. I know that this distance, for example, is 2 meters, and this one is 1 meter, and there's another 1 meter. Okay? So I know that this is 2 meters, and this is 1 meter. How about this? This is something that isn't changing. I'm gonna assume it's a variable. S is it changing? Okay? Can you guys give me S as a function of theta? How? How can I do it? It was the cosine rule. How it's gonna be? If you guys remember from the law of cosines, so S is equal to this square plus this square minus 2 this by the cosine theta. Okay, so this S, I'm not sure if you guys remember this or not. So it's gonna be 2 squared plus 1 squared minus 2 multiplied by this dimension 2 by this dimension 1 cosine the angle between them, which is theta. We can do it actually in a different way. It's gonna be a little bit long. You can get this triangle and make it right angle, and you know that this is gonna be 1 sine theta, and this one is gonna be 1 cosine theta. This is gonna be 2 minus 1 cosine theta, right? This part. For this triangle, S is gonna be equal to, or S squared, this actually is squared. It's gonna be 1 sine theta squared plus 2 minus 1 cosine theta squared. Let's do that. This is gonna give me sine squared theta plus 4 plus cosine squared theta minus 2 multiplied by 2 multiplied by cosine theta. So this is gonna give me, what is cosine squared plus sine squared? It's 1. And this 4 is 2 squared minus 2 multiplied by 2 multiplied by cosine theta. So it's gonna give you the same thing by geometry. Alright, so right now I know actually s as a function of cosine. So you know s squared is gonna be equal to 5 minus 4 cosine theta. I have s as a function of theta. So right now I want to convert this linear arm to velocity and acceleration and all this part. How can I do this? To convert s to velocity, you need to differentiate with time. To acceleration, you need to differentiate another time. So if you differentiate this, it's going to be equal to 2, let's differentiate d dt. You guys tell me, what is going to be? 2s and multiplied by? We differentiate with respect to the time, not 2s. So, if you guys remember, we need to have ds, dt at the end. But if I'm differentiating this, dds, it's going to be 2s only, because ds is going to be 1. Equal to 5, what is the derivative of 5 with respect to time? 0. And then we will have negative 4. What is the derivative of cosine? Negative sine theta multiplied by d theta dt, because I need to take the derivative of what is inside. So this is going to leave us, what is ds dt is the velocity. So you have ds multiplied by the velocity is equal to 4 sine theta multiplied by omega. Okay? Alright? We differentiate d dt one more time so that we can have acceleration inside our problem. So you have two components, you need to get the derivative for them. 2s is going to be 2 multiplied by ds dt multiplied by v. So I drive the first one multiplied by the second one, plus the derivative of the second one multiplied by the first one. So we'll have 2s dv dt. Then this one I have 2 components, sine theta and omega. I'm going to differentiate this. It's going to be 4 cosine theta d theta dt multiplied by omega plus 4 sine theta multiplied by d omega dt. Do you guys know what I'm doing?
Yeah.
I have 2 quantities. I take the derivative of the first multiplied by the second multiplied by the first. Do the same thing over here. Next time I'm gonna continue in this problem. It's almost done, but I'm gonna do it again, just like refresh your memory.
The last one 0. Isn't ds dt is 0?
No, this is the same thing.
Oh yeah.
Ya, ya,